So I have started the
Okay.
recording now. So thank you guys for joining to this session. So like you guys already know, we want to have some kind of tech talks, and basically the main plan is to share technical ideas, our experiences with the projects that we have, and like maybe have a casual discussion with each other, so that we can learn from each other's mistake, we can learn from each other whatever we are doing good, so that it can be helpful not only in Monstarlab but in future as well. And for the time being, like we are expanding this to Bangladesh and Philippines, but in future we will like to expand these to other branches as well. And this will be going on trial basis. So if there is any feedback from you guys, do let us know. We'll be happy to make it better together with the help of you guys. So thank you again. Just regarding today's talk, as you have already seen, Milan will be talking about Elixir. So yeah, and that's a really exciting topic and something new that we'll be getting to learn. Just a small update in case we miss to give the announcement later on. So we'll be having our next session. It was supposed to be on 22nd because we'll be having our session every 2 weeks. But 22nd is holiday on Japan side, so we have to skip that, and we'll be having that the following session that we have. That's probably on August 5. So I'll be giving the announcement over Slack as well. So without further ado, I will give the floor to Milan. So Milan, go ahead.
Thank you so much. And thank you all again for joining this Tech Talk, the first one focused on backend. I hope you can see my screen, fingers crossed that's working. And if so, I would like to talk about Elixir today. Elixir is a functional programming language, and I subjectively feel it's very powerful, incredibly fast, and very beautiful programming language. Or as I like to call it, and to keep in with my personal silly theme of having multiple title cards for no apparent reason, Elixir is a magical cure for all of your programming needs. And before I dive deep into it, I want to give you a little preface as to what inspired me for this talk. A couple months ago, I really fell in love with Elixir, as many of you know, mostly because I can't seem to shut up about it. Sorry, but not sorry. Contrary to popular belief, I actually really like to try new programming languages, just like many of you guys. And Monstarlab really gives you a great opportunity for that, because it exposes you to so many different languages. So over the course of the past 3 years that I worked at Monstarlab, I got experience with a couple of languages. I liked a few, I hated most, but that's just because I'm picky like that and I know what I like and especially what I don't like. Among the ones that really intrigued me was Ruby, shining above the rest of them all, because Ruby felt to me personally like it is a very powerful language, but at the same time, it was very beautiful language. And Elixir comes from the same background, because when Elixir was being created, it basically looked at the Ruby syntax and it said, I would like some of that. So it is very heavily inspired by Ruby syntax. If you joined the Monstarlab Borderless Engineering Conference a couple of weeks ago, you already know about one language that is also very similar to Ruby. That is, of course, Crystal. Now, I consider both Crystal and Elixir to be Ruby's little sisters. And I would like to pitch Elixir for you today and try to convince you that it is worth your time. The first thing I mentioned about Elixir is that it is a functional programming language that is very contrasting to what we are used to in our daily business, and it may seem a little bit scary at first. You've probably heard of functional programming. I mean, whenever you go on the internet, people will probably be claiming and have been claiming for the past 5, 10, 20 years that functional programming is the future, pretty much in the same way as the next year is going to be the year of Linux on desktop. Now, I don't know about Linux on desktop, but with functional programming, the premise is actually fairly strong. Functional programming promises us to build better maintainable, more safe, more reliable, more composable applications that are easily testable and fairly easy to reason about. There have been even done academic studies that compares two of the same applications, one written in a functional declarative approach and one written in the traditional imperative approach. While these two applications had the exact same functionality, to write the functional version, the programmers needed to use sometimes as little as 4 and sometimes as little as 20 times less code. So the promise is strong, but I don't know how about you, but I have tried a couple of existing functional programming languages in the past. I tried Clojure, which is essentially Lisp running on Java virtual machine. But I gave up after a couple of days. It was just not compatible with this old brain here. I tried Haskell, but honestly, I gave up so quickly that I only remember the name Haskell and nothing else. I also tried Scala, but I tried it by opening documentation and then having similar reaction to when my wife tries to give me vegetable on my plate. No, thank you. Get that thing away from me. Not interested. So it's not that functional programming as a concept is not a great idea. I still think it really can be. It's just honest talk. I think that the existing programming language is kind of suck. But Elixir is here, coming to the room, storming with great parade and saying, it doesn't have to be this way. Functional programming can be fun. Let's all have fun together. Before we have a look at Elixir, let's make sure we are all on the same page. So let's talk about functional programming for just a moment. In your traditional imperative approach, you're writing fairly low-level code. You're telling your computer essentially line by line what kind of thing it should do and what it needs to execute. In that sense, you're essentially writing a little cookbook for your computer. You're saying put some milk in there, some sugar there, and some salt there, mix it all up, and at the end you may get a delicious cake. Or it may just all blow up in your face. In functional programming, that's not really what you're going to be doing majority of the time. Rather, you will be building a decision trees composed out of small, reusable, composable, testable, simple functions that your data navigates through from some point of input and gets transformed on the way until it reaches some output that we desire. Honestly, when I heard this definition for the first time, I was not all that impressed. My thinking was something like this. Okay, I can imagine this if I'm writing something very simple, like a CLI utility. Executing it in a shell or in a terminal if you like. I get some input from the user, I do some transformation of the data, and I spit out output. Fine, I can imagine that. But how does it relate to the things that we actually do every day, that is writing our backend servers? Well, it actually transforms fairly well, because all we are doing when we are writing backend servers is we are getting some data on the input, typically in the form of an HTTP request. We look at the data, we plug some HTTP header there and some path parameter there and some JSON values from there. We transform the data through database calls, through calling third-party APIs, through doing some sort of computation, and slowly transforming the original HTTP request and amending it so that the next function in a row can work with the intermediate data that we just computed, until at the end we no longer have an HTTP request, but rather we've got an HTTP response we can return back to the user. Functional programming builds on a couple of core concepts that we need to talk about. It requires the language to support functions as first class and also have higher order functions. It encourages you to write as much code as a pure function. It wants you to loop through sequences using recursion, and it really wants you to have all data immutable. Let's have a look at these concepts in detail. First-class function just means that functions are treated as a first-class citizens and therefore can appear anywhere else that other first-class entities can. Typically, that means you can assign an anonymous function into a variable, and you can pass a function to another function. Higher order functions builds on top of that concept, and it says that higher order function is any function that takes other function as an argument or returns other function as a result. You've got, of course, your holy trinity of higher order functions, your map, your reduce, and your filter. Your map will transform one element of an input sequence into one element of an output sequence. Filter lets only certain elements of the input sequence appear in the output sequence. Reduce, or as some like to call it inject or fold, will transform the entirety of the input sequence into a single element on the output. Now, granted, recently both of those trends have been becoming more common even in imperative languages, but there are still languages that don't support this whatsoever. And even when taking this concept in a traditionally imperative language, there may be some downsides. When it comes to pure functions, at first, maybe writing a pure function will feel like a little bit of writing with handcuffs on your hands. But eventually, you will realize that these handcuffs give you a great level of freedom and peace of mind. Pure function introduces and relies on no side effects whatsoever. It does not modify memory outside of its execution loop. It does not need data from I/O and doesn't write data into I/O either. It does not communicate with databases nor third-party server or essentially anything that has any chance whatsoever to fail. Now, of course, not all functions can be written as a pure functions. Technically, side effect is what we are really getting paid for. Our clients really care about side effects. That's for them, it's the result. They don't care about our clean code. But if you write as much of your code base as a pure function and group all of your pure functions into one side of the application and then all of your impure functions into tiny little garden where you isolate them, well, that gives you absolutely amazing code base to maintain in the future. And it also allows the optimizer to do some pretty cool optimizations for you. Optimizations such as, if there are no side effects, then calling the same function twice with the same input necessarily has to produce the same output. Therefore, you can cache the output and you don't need to execute any function twice. More importantly, if there is no data dependency between two pure expressions, well, then their order of execution can just as well be reversed if that is beneficial for the CPU architecture you're running on, or they can be executed in parallel, giving you parallel execution for free. On the topic of recursion, if you will try to search for your traditional whiles and do whiles and for eaches in a functional language, well, I don't think you're going to be very successful. Functional languages instead want you to iterate through sequences via recursion. The recursion can be either having the form of a direct recursion in which the function calls itself, or it can have the form of an indirect recursion in which the function A calls function B calls function A then calls again function B, and if I'm not going to stop here, we're going to be here for a very long time because I clearly did not implement the base case in this recursion to help me exit out of it. Now, having a base case is, of course, very important, as you will find on the internet. I would just like to enhance this advice to have a reachable base case. I think that's even better. Now, you may think, okay, I can maybe handle a recursion if you really want me to, but in the past, anytime I tried, I run into some memory issues, or my application just crashed altogether via the famous Stack Overflow error. And while that is a real issue for augmenting recursion, this is not necessarily something that you cannot avoid, because you can rewrite any augmenting recursion into a tail called optimized recursion, or as their friends like to call it, just a tail recursion for short. Let's have a look at how that kind of recursion would look like. So here you've got your first exposure to a larger piece of Elixir code. I'm sorry for throwing you into the water, but I'm going to try to do my very best to help you swim. I hope you can see at least my cursor here, fingers crossed. So I'm going to be pointing at little parts of the code as we go. Here we are having an augmenting recursion. We define a module called math, where module is just a home for any function that you define. In the module, I'm defining a function called sum. It may look like I'm defining the function twice, but the function is actually defined only once. It's just that it has two clauses. Clauses, what's that all about? Well, you may think as clauses as kind of your function overloading on steroids. So in your typical imperative language, any self-respecting language, you may overload any function by having different number of arguments, of course, or you may overload it on the types of the arguments. Well, you can do so in functional languages as well, but typically you can also overload on exactly the shape of the data that gets passed, or if you want, on the value of data that gets passed in. So here we are defining the sum function with two clauses. The first clause will get executed if we pass in an empty list. The sum for an empty list, of course, has the value of 0. Very declarative, very intuitive, I would say. Now for a non-empty list, we are looking at the list and separating the head of the list from the tail of the list. Now, what is head and tail? Head is just simply the first element of a list, while tail is a list of all of the remaining elements. In the example here below, the first element, the head, would be, of course, 1, and the tail would be the list of 2, 3, and 4. Therefore, the sum in the first iteration would be defined as head 1 plus the sum of tail, that is sum of 2, 3, and 4. In the next iteration, our head would move one position to the right, therefore it would have the value of 2, and the tail would be also shortened to just the list of 3 and 4. The same would happen in the next step, until in the final step, we would now have head with the value of 4, and tail would be an empty list. Therefore, the sum is 4 plus the sum of an empty list. We previously already defined what the sum of an empty list is. That is, of course, 0. Therefore, we evaluated all of the variables we need, and we can unwind the stack and get the result back. That's 0 plus 4 plus 3 plus 2 plus 1 equals 10. That is very declarative, and again, that is probably the recursion you will be most familiar with, and that you may use any time that you're going to be looping through a limited number of elements and you're not running into Stack Overflow issue. If, however, you feel like the Stack Overflow risk is too big, you may anytime switch to a tail called optimized recursion by rewriting it just a little bit. Tail called optimized recursion is defined as any recursion that ends with a function call. The last full expression, the last full statement has to be a function call. Now you may think, but wait, you already have a function call as your last statement here. So what's this all about? Well, that's not a full statement though, because the full statement relies on the plus operator here. We need to somehow get rid of that. We can get rid of it by rewriting the recursion into 2 functions, this time for real, 2 different functions. The external interface, the public function, will remain exactly the same, so there is no change for any consumers of our simple math API. The public function will execute a private function, which takes 2 arguments. The first one will always hold the intermediate value of sum, which will be slowly increasing as we process through the list. The second argument will then hold the ever so shortening, ever so decreasing tail of the list that contains all of the elements that are not yet included in the summation. The private function yet again defines 2 clauses. The first is defined for an empty list. If we are calculating sum for an empty list, well, then we can just return the value of the first argument, which contains the sum. That can either be the 0, or it can be some value from previous iteration of this loop. The second clause is more interesting. It, of course, is defined for a non-empty list, where yet again, we are separating the head from the tail. And we are saying that we need to call the same function yet again, but this time enhance the sum with the value of head. If we go through the small example of list of 1, 2, 3, in the first iteration, the sum will be 0. That's coming, of course, from here, from this point. The head will have the value of 1. That's the first element of our list. Therefore, 0 plus 1, that's 1. And the tail for the next iteration is a list of 2 and 3. In the second iteration, the sum will already start at the value of 1, passed from the previous iteration. The head will start with the value of 2. 1 plus 2 equals 3, and the tail is now just a list of a single element of element 3. In the final iteration, sum is already pre-calculated as 3, of course, from previous iteration, and the new value of head is 3 as well. 3 plus 3 equals 6, and the tail is now an empty list since we reached the end of the original list. We already know how the sum for an empty list is defined, therefore we can just return the sum in the first argument, that's the 6 being held right here. Since the last full expression of the function is a function call, again, this is a tail called optimized recursion that can loop forever. It will not consume any additional memory with each loop, and it will not run into Stack Overflow issue. The final concept of functional programming is the concept of immutable data. All data is treated as immutable, and if you want to modify it, you have to transform it with a new copy. Now that may seem incredibly wasteful, and it is just a little bit wasteful. There are heavy optimization done both on the compiler and the runtime side so that data is reused as much as possible. In this example, we are defining a tuple being a collection of fixed number of elements. It's called, or is being held in the variable called a tuple, and it contains values a, b, and c. If we look at the representation in memory, it may look something like that. It just points at the values in memory a, b, and c. Now say we want to replace the element on the second position, that is index 1. From b, we want to switch to b2. We can do so by calling the putlm function on the original a tuple with the index 1 and the new value b2. The original a tuple will of course not be modified because all data is immutable. Rather, the putlm function will return a new tuple that is modified. In memory, however, the position of the first and third element will not occupy any new space because the value of A and C that are previously in memory already stored can just be reused, and only B2 has to be put in the stack. Now, how can we do so? Well, we can do so very easily because we know that nothing will ever change the values of A and C under our nose because, yet again, data is immutable. It's a self-solving problem. This helps us immensely with things like thread safety or with race conditions. It also gives you kind of a safety net. Imagine you've got a large function that does some sort of computation on a data passed into the function. You do some computation, but in the middle, while you're modifying the data, your function unfortunately crashes. That may happen, but what's the state of data from the point of the caller of the function? Is the data now corrupted because it was half processed and half not? What to do? How do we recover from this? Well, there's not even recovery needed because all of the computation was, of course, being done on a copy. This essentially gives you a rollback on the code level rather than database level. Now, with that covered, we can finally talk about Elixir, except, sorry, we can't because we need to make one last detour. That detour is into a station called Erlang. The reason for this is that the relationship between Elixir and Erlang is just about the same as the relationship between Kotlin and Java, in the sense that Elixir runs on Erlang virtual machine. Erlang is what powers a lot of Elixir's awesomeness, so let's talk about it for a few minutes. Erlang was developed over 35 years ago by Swedish massive company Ericsson. They are absolute giant in the telecom industry, and in the 1980s they were building new generation of telephone switches. And let me just give you some context. At that time, that was one of the most complicated systems and IT problems out there, compared in complexity only to the internet of today. For programming those telephone switches, they needed a language that would allow them to develop highly available, concurrent, distributed, fault-tolerant applications. The language would have to support high concurrency and absolutely zero downtime, even during deploys. Now, they spent a couple of years doing research. I mean, who wouldn't want to do that? Lucky engineers out there. And after a couple of years spent by looking at all of the languages available at that time, they came to the conclusion that while languages are kind of cool, and some of them even have features that they would want, there is not a single programming language that would have all of the features that they required. Therefore, they are left with no other choice but to write the language themselves. They did not stop just at writing a language, they wrote an entire platform. Erlang is not just a programming language, it consists out of at least 3 parts, arguably 4, but let's keep it simple with 3. The first part is the programming language itself, and fortunately, we can very much skip it and not talk about it, kind of pretend it doesn't exist, because unfortunately, it very much follows the pattern of other functional programming languages in the sense that it kind of sucks. It's fine, but it has very high barrier of entry. The syntax is kind of alien for most of us. The other 2 parts, however, of the entire package are way more awesome. The first part, or the second part, is called Open Telecom Platform, which is a terrible name for a wonderful thing. It has nothing to do with the telecom industry nor programming telephone switches. Rather, it is a set of libraries, tools, principles, and best practices as to how to build resilient and reliable applications. It has been battle tested in production all the way across the world for the past 30 years, so you should use the knowledge gathered there as much as possible. Finally, the last part of the package is the Beam virtual machine, and I'm going to be talking about Beam in just a moment, but let me just spoil it a little bit. I did some Java development in the past, and while of course everybody knows that Java runs on Java Virtual Machine and is not compiled to native code, rather it's compiled to bytecode, and bytecode runs on Java Virtual Machine and blah, blah, blah. Everybody knows that, but I never, maybe that's just my stupidity, I'm not denying that, but as a developer, I never really knew what Java as a virtual machine brings to me as a developer as a benefit. Now here in the case of Beam virtual machine, which let me just say Beam, that's a pretty cool name. Beam virtual machine gives you benefits that you will actually see. One more thing to mention about Erlang when they were developing it and thinking about what the language should be all about is that the engineers were considering very strongly how to deal with failure and errors. Now, many languages today will require you to deal with errors on your own. They will either have you check for some error state at all times, or in more sensible scenarios, they will throw an exception and have you as a developer to deal with that. Now, that's not going to be the case in Erlang or Elixir because the engineers out there decided that failure is inevitable. It will sometimes just happen, and defensive programming is kind of just a waste of time. So rather than focusing on how to prevent an error from happening, they decided to spend enormous efforts on being able to recover from an error and from a crash. The motto of Erlang is let it crash, and that doesn't mean that crash should affect end user. That's not the case. It's just that crashes will happen, they may happen, they will happen, but they should be isolated to the smallest possible part of the entire system, and they should be easy to recover from. Erlang is a process-oriented language. It encourages you to separate your application into lots of tiny, isolated, lightweight processes that communicate with each other through messages. And you may be thinking, wait a second, weird boy, that's not what my university professor told me. They said that processes are very heavy and context switching is expensive. And while that is certainly true, here we are not talking about operating system level processes. We are rather talking about Erlang level processes, which is way more granular than even threads. They're fast to create and very light on memory. You can easily spawn hundreds of thousands of processes within less than a second. And your typical Erlang or Elixir application will have hundreds of them running at all times. And it's easily possible to have tens of millions of them. I mean, try doing that with threads and then come back to me because I really want to see your face when you fail. Processes can receive messages and respond by creating new processes, sending messages to other processes, or modifying their own internal state. The state is, of course, still immutable, but there is a way to simulate a mutable state in a safe way. Now, what is amazing and one of the tangible benefits of the Beam virtual machine is that it does not matter where the target process you want to communicate with is running. It can run locally on the same Beam virtual machine, or it can run on different virtual machine in the same network on different physical machine, or it can run all the way across the world. And just through being connected to a cluster of Beam virtual machines, you still communicate with your processes all the same. You don't, as a developer, you don't have to write a single line of code that handles with network communication. All of the process messaging is handled for you. And Beam just makes sure that the message is properly delivered. You don't have to worry about process discovery or service discovery either. That's already pretty amazing, but just think about this in a grand scheme of things. Nobody says that your servers will all be running the same architecture. You may have majority servers running AMD 64, but maybe in some closet, you're going to have some old PowerPC server joining the cluster. Now, these two architectures, if I'm not mistaken, they use different endianity. So they represent things internally very differently. Even numbers are represented differently on a bit level. Again, you as a developer don't need to worry about that whatsoever because Beam abstracts all of this for you. You just say that you want to send a message to this target process and the message gets delivered. All of the differences between architectures that gets abstracted away. And nobody's of course saying that you have to send numbers as a message either. You can send literally anything. You can send strings. You can send even entire functions. This allows it to easily scale both horizontally by adding more machines into cluster and distributing the load that way, or of course vertically by adding more cores. All of this happens extremely quickly as well, because Erlang spent over 30 years of doing one of the best preemptive scheduling that is out there. With this preemptive scheduling, one process cannot affect the latency of other processes, and there's effort from the Beam virtual machine to keep the average execution time of any given function relatively consistent, even under a heavy load. The cheapest VPS servers can easily get you 2,000 requests per second. And again, try doing this with Rails or vanilla Laravel, which will struggle with 200 requests per second in some scenarios. I mentioned before that if you're writing an Erlang application, it will be basically split into a bunch of processes. Now, bunch is not a very scientific word, so let's replace it with more appropriate. It's going to be a tree of processes. Tree because processes should be supervised so that somebody can handle with the failures that may happen along the way. That someone is called supervisor, and supervisors have their own restart strategy for dealing with failure in a worker process. When error happens, supervisor may decide that the error is best handled by just restarting that process and trying again. Or it may decide that the failure was not with the process itself, but rather some other child process and restart that process as well. It may also determine that the failure was coming from somewhere else in the system and crash on its own, letting its own supervisor handle the entire situation. Kind of cowardly, but it works. Now you may be thinking, all right, you keep claiming here that Erlang is so amazing, so why don't people use it? Well, the thing is, people keep actually using it and have been for a very long time. The thing is, I think it's kind of a very well kept secret in the IT industry, because if you have ever used chat applications such as WeChat or WhatsApp, well, these are written in Erlang. WeChat, of course, being the world's third largest messaging platform, and WhatsApp dealing or handling well over 2 million concurrent connections 10 years ago from a single physical machine, just thanks to the power of Erlang. If you had to deal with queue system, well, then you will know that RabbitMQ is written in Erlang and uses the benefits of the scheduling for quick delivery. In the telecom industry, we cannot mention again Ericsson, because Ericsson, with its over 40% market share and its hands in the GPRS, 3G, 4G, 5G, whatever G infrastructure all over the world, means that there is a high likelihood that the IP address assigned to your mobile phone today was assigned by a program written in Erlang. In the healthcare industry, we've got the UK's National Health System managing over 965 million daily requests with over 99.999% availability over the last 5 years. In the advertisement industry, we've got no less impressive AdRoll, which handles well over 500,000 real-time bid requests per second. That is average, not a spike. In the gaming industry, we've got Nintendo, which uses Erlang to handle millions of concurrent connections from their Switch console, and finally Riot Games with their League of Legends and over 7.5 concurrent players at any given time. So it's not that Erlang is not being used, it's just that maybe it's not as popular as it should be. And maybe that could be due to the Erlang as a programming language. And maybe if that is the case, then we can probably fix that with the help of Elixir, which aims to use all of the benefits of the Erlang platform and leverage it to new heights with replacement as a language on the Beam virtual machine. Elixir was written by Joseph Valim in 2011, and it tries to be a modern, very approachable Ruby-like language. It has 100% interoperability with Erlang, giving you all of the benefits of the Erlang platform while not being limited to it. It can still bring new features to the table, features such as function piping or very powerful meta programming, which allows you to generate new code on compile time. Now, when introducing new language to a new audience, which may have not heard about it before, because let's be honest, this is not one of your mainstream languages, I was thinking that there's probably two approaches I can take here. I can either go from the very basics, kind of boring, but basics, and slowly build the knowledge up. I can also just throw you into the most amazing features, but risk losing you 5 minutes in because it may not be comprehensible enough. So I was thinking, let's try combining these two approaches together, and let's look at one boring, one amazing, one boring, one amazing feature as we go. And so let's start with something boring, which is types. Except even with types, there's something kind of interesting happening here. You've got your value types, your system types, and collection types. For value types, integers are kind of interesting in the sense that you don't need to worry about using int 8 or int 16 or int 64. They change their size appropriately as you go, and there is absolutely no limit as to how big they can get. I've never seen that before. Correct me if I'm wrong. Atoms are very similar to Ruby's symbols in the sense that they are super well optimized, and it's a data type in which the name equals its value. You're gonna see them sprinkled all over Elixir and Erlang ecosystem. Now, collection types for me are the most interesting one, probably. So you've got your tuples, which is the closest thing you're gonna get to an array. It's a fixed size collection. Lists are implemented as a linked list, and a map is your go-to data structure for any sort of structured data. Now, when it comes to maps, you can use anything as a key. If you use atom as a key, you can use the shorthand syntax with the colon, just like in Ruby. If you decide to use anything else other than atom, such as string, number, or even function, nobody's stopping you, then you can do so, but you have to use a little bit longer, but admittedly more cool hash rocket syntax. Finally, binaries are typically, you're gonna meet them mostly as a Unicode strings, but not limited to. Elixir is really amazing at handling binary data, which otherwise was always very scary for me to deal with, but Elixir is some pretty amazing tool to help you deal with that. And with a boring topic out of the way, let's jump into something more amazing. He said, as he switched to a slide which assigns a value to a variable. Got you there. Except this is not really an assignment. We call this value binding or variable binding. That's because this is not your typical assignment operator. This is a pattern match operator. The only job of pattern match operator is to make sure that the left-hand side is equal to the right-hand side, and it can do so with any way imaginable. So that while this is a valid syntax, this is also a valid syntax. Well, that's not something that's going to really fly in any other programming language, I would think. But here it makes complete sense because A gets substituted to the existing value of 1, and it just gets matched because it can perform that match without any problems. If you, however, try to force our little matching operator to do something that is impossible, such as matching 2 to 1, well, then no matter how the match operator is going to try to do, it will never succeed and it will give you match error. We can also use the match operator to rebind value for a variable into new value. And you may think, okay, so you completely just undermined your statement about immutable state. What's this all about? Well, no, this still means that the value 1 will exist still somewhere in the memory. As long as something else is still referencing it, it will remain unchanged. However, we can rebind variables into a new value. If you want to necessarily consider the value of a variable while pattern matching, you can do so with the help of a pin operator. In this case, the matching will fail because 2 will not equal to 3, no matter what you do. Now, and on to something even more interesting, because there's so many different uses of pattern matching, you can use pattern matching like so. First, we bind the list of 1, 2, 3 into a variable called list. Later, we use pattern matching to extract these values out of the list so that A has the value of 1, B has the value of 2, and if I could fit it on the screen, you would see that also C has the value of 3. Just have to use your imagination here. You don't need to use pattern matching only to assign or to bind values into variables. You can also use it to match on the shape of the data, like so. Here we continue to bind values into variables A and C, but you're saying that you require the second element to have the value of 2. If you try to match on a pattern that will not match, you will yet again end up with a match error. Now, for me, probably the most cool usage of pattern matching is pattern matching with functions. You've seen a similar example before, but what kind of talk about functional programming language would this be if we did not have at least one implementation of factorial? So here we go. Here we define yet again a single function with 2 different clauses, and we are matching on the shape of the data coming in. In the first clause, we are matching on the shape 0 or on the value of 0. Factorial for 0 is defined as 1. That is as declarative as this gets. This just reads amazingly. If we cannot match on the value of 0, we just bind the value into variable n and perform appropriate computation. Now you may be a little bit confused about this comma, space, do, colon, space, what's that all about? Well, that's just a shorthand syntax for one-liner functions. Your functions will very often be one-liners, and you can save some typing and some space in your source files like so. But if you're more familiar with the Ruby-like block syntax, then you can still keep doing it with the Ruby style. Nobody's stopping you there. There's one important thing to consider while defining multi-clause function, and that is that the first matching clause will get executed and only the first one. Therefore, the order of the clauses matter. This is fine, but if we switch the order like so, this is not fine anymore, because if we pass the value of 0, then even the first clause will match and it will give us an infinite loop. The second clause will never match, and that may seem scary until you realize that the compiler will realize this for you, and it will tell you that you're trying to do something very silly. Now, if I go back to the original definition of factorial, you may also think that, okay, nice, this works kind of, but what if I pass a float in there, or a string in there, or what if I pass a negative number? So pattern matching already allows you to limit what kind of data gets executed and what kind of clause is the one that will run. But if you want to limit the execution scope even further, you can do so with guard clauses. They look like so. They are located after the list of arguments, but before the do keyword. And they allow you to inspect the data that is coming in. If the guard clause evaluates truthfully, then the clause gets executed. Therefore, here we are requiring the value to be an integer and also a positive one. Now, in this case, if we pass a string or a negative value, neither of these clauses will match, and we end up with a match error, which may result in a crash. But again, crashing is fine in these kind of scenarios because we can recover from them. Now, since I'm running a little bit out of time, that's what I kind of expected, I'm going to breeze through rocket speed through the next couple of slides. Guard clauses and pattern matching already gives you pretty amazing capabilities of controlling the flow of execution of your application. It essentially replaces your if-else statements, your switches. It replaces your loops because we've got your recursion. But if you want to return for a little bit into the imperative world, the ifs are still there, and sometimes, sure, they are more easier or more expressive to use as well. If you're coming from the Ruby world, unless is also joining the party. Another statement for controlling flow of execution is condition, which essentially serves as either your switch statement or your if, else if, else if, else if, else statement, in which the first matching condition will be executed. Final control flow statement, or definitely macro, but that's an implementation detail, is a case which looks at the data being passed and it tries to find the first matching pattern. Here we are requiring the map that comes in to have a key of name age. If it has age, then this clause gets executed. Elixir, of course, has support for anonymous function. It's a functional language after all, so you can define an anonymous function like so and bind it into a variable. What is, I think, more interesting is that even anonymous function can have multiple clauses, so it can again inspect the data coming in and execute different code based on the data. Here we are defining a file open handler, which matches on the shape of the incoming data. If it's a tuple with the first element of atom of OK, meaning that the file opening succeeded, then we read the first line of the file. If this clause does not execute, then the second will surely match, and we get an error description as a result. Now, one of the most stable functions of Elixir is how it handles multiple function calls that depend on one another. In this example, let's say that we are finding customers from database and binding it into this variable. And then for each customer, we are finding their orders. And then for each order, we are calculating the sales tax based on the sales rate in the year 2018. And then finally, we prepare filings for the tax collected. And while there's nothing technically wrong with this code, it's a little bit unwieldy because we are binding three variables only to be used in the next statement and only the next statement alone. Now, other functional programming languages would probably solve this like so by combining all of those function calls into a single statement, but I think that's way more terrible because in order to understand what is happening here and decipher it, you have to start reading from the middle. This is really the first statement that gets executed, and then you have to continue reading to the top. I think this is straight up crazy and should be really illegal. Elixir thinks similarly, so it introduces a function piping operator. It allows you to compose your functions in an absolutely amazing way. You can still continue reading your code from top to bottom, but when you find customers from the database, this function returns the customers. Following is a function pipe operator. Function pipe operator will take a result of the operation on the left-hand side, and it will pass it as a first argument to the function on the right-hand side. And similarly, here we fetch the orders for our customers, and through another function pipe, we pipe it into the sales tax function. Again, here it's passed as a first argument before the 2018. Now let me just tell you and kind of promise you that when you start writing your own pipelines of functions that interact with each other and you start writing this sort of code, you will feel honestly like a god, if that's not your normal state of being, that is. Now your final feature of Elixir I want to cover here today is the absolutely amazing support for concurrency and parallelism. So in this example, we've got function which receives a big list of emails. It breaks it with one line of code into chunks of 100, and then it sends emails of the 100 batches asynchronously, while still making sure that only maximum 20 of those batches kept running at a time, let's say because our email sending provider has that sort of API rate limit. This is so readable and so easy to do, but it accomplishes so much. Like this concept of transparent parallelism and concurrency is really what brought me to Elixir. Let's briefly look at some success stories for Elixir. You may have heard of small companies such as Heroku, Pinterest, or WhatsApp. Square Enix uses Elixir for their user authentication, CMS, and APIs. If you use Discord, well, that is written almost entirely in Elixir as well. And Bleacher Report is a notable example because while I know nothing about sports and Bleacher Report is a sports website, I find their migration from Ruby to Elixir absolutely mind-blowing because during the process of migration, they managed to keep all the functionality up, of course, but they reduced the number of servers that their website was running on from 150 to just 5. What is Elixir good for, therefore? It is amazing for web development using the Phoenix framework. It is recently gaining a lot of ground in the IoT with Project Nerves, which allows you to take your Elixir code and build it in the form of firmware that you can start your IoT device with. Finally, recently, in just February of this year, there was announced Project Numerical Elixir, which hopes to bring Elixir into the field of machine learning. Now, our last stop on this journey, with the last couple of minutes I've got left, I want to bring your attention to Phoenix specifically, because that's probably why you're going to be interested in Elixir for the web development purposes. So Phoenix is the leading web framework in the Elixir ecosystem. Is your full-blown batteries included ecosystem framework. It has all of the powers you would expect from any other web framework. Your router and your controllers and your views, all of that is in there. Your ORM is there. Your server-side HTML rendering is there. Everything that you are hoping for will likely be there, middlewares included. Just like Rails, from which it takes heavy inspiration, it prefers convention over configuration, but with the catch that it hides nothing from you and it wants you to be able to always customize and understand everything. Phoenix is what I would call the first, or maybe I'm not informed enough, but for me, it's the first multi-paradigm framework, because while you are rarely limited in what your web framework allows you to do. You can do pretty much anything in your Spring Boots and in your Laravels and your Railses and Vapors. Oftentimes, it feels like maybe one way is just a little bit better. If you're developing in the Vapor framework, you can do your REST APIs absolutely wonderfully, right? But if you try to do server-side rendering, it feels a little bit clunky. And if you try to do GraphQL APIs, you're gonna probably not have a very good time. Similarly, you can do amazing things in Rails. You can do your REST APIs and GraphQL APIs, no problem whatsoever. But for me personally, it still always felt that Rails is a little bit more developed in the field of server-side rendering. But in Phoenix, there's a combination of a couple of paradigms, and it never felt to me that one is more preferred or more developed than the other. There's, of course, your traditional server-side rendered websites using embedded Elixir, which is super similar to embedded Ruby. You can develop your REST APIs without any issues, and there's incredibly powerful Absinthe framework for helping you with GraphQL APIs and all sorts of problems that you may run into, such as elimination of the n+1 problem, kind of automatically. It's really amazing. Now, these are very common in all other frameworks. What you will see quite less often is Phoenix says that web is more increasingly, especially recently, all about real-time interaction with the user. User should not be waiting until HTTP request hits the server, gets executed, and gets returned back, even in the form of, let's say, a single-page application. Phoenix says that for a lot of purposes, there's a much better way, and that is with Phoenix channels. These are implemented typically through WebSockets. And again, I've never seen a framework, again, please enlighten me and tell me I'm so wrong, that treats WebSockets connections with such level of grace and elegancy as it does with all their other REST APIs. Similar to what WhatsApp did 10 years ago, where they managed to do 2 million connections on a single machine, the Phoenix team decided to do similar tests in way more higher level, that is in Phoenix, and they were still able to achieve 2 million concurrent connections, that is WebSocket connections, over Phoenix channels. Now, finally, there's a new way of writing your websites using Phoenix Live View, in which you can write interactive websites without having to write a single line of JavaScript yourself, which, if you ask me, that's a super interesting promise, because we would want to write JavaScript, right? So they are server-side rendered, but while rendered on the server, the websites written in live view are still dynamic and interactive. They can react to user events, and they can react to changes in your database as well. How does that work? It's basically like an Elixir in browser, because you're not writing JavaScript, or the code kind of looks like you're writing React, but executing it on server. So it really works by rendering the final HTML on the server and keeping track on what the user is doing and what the user should be seeing on the server. Anytime the web page changes just a little bit, the server computes a diff between the two HTMLs, the one that user is seeing and the one that user should be seeing, and it sends it back to user's browser through WebSockets. On the browser side, there's actually a tiny bit of JavaScript, but nothing you have to write yourself. That's a part of Phoenix, which takes that incoming data through WebSockets, interprets it, and changes DOM according to the diff that arrived from the server. That's pretty amazing, but you may be thinking, is it scalable? And it actually is. The creators of Phoenix, they created this demo that does 60 FPS animation rendered on server, and every 1/60th of a second, it sends over WebSockets the new frame of that animation to user's browser. Absolutely mind-blowing. In Phoenix, you will often encounter what's called the petal stack, where the P and E stands for Phoenix and Elixir, obviously. T is used for Tailwind CSS for writing CSS inside HTML while retaining your sanity. If you sometimes need a little bit of JavaScript because not everything is yet possible to do in live view, it's a very new technology, you will probably sprinkle a little bit of Alpine JS there and there to help where live view is not enough. Finally, live view for server-side rendering and most interactions. With that, I'm pretty much out of time, so I would like to thank you for your attention. And if any of this seemed interesting at all, I would highly encourage you to join the newly created channel on Slack called Working Group Elixir. Just yesterday evening, I posted a couple of introductory videos there from people way smarter than me that explain different parts of Elixir and Erlang. I would especially want to focus your attention to one video which is just 15 minutes in length, and it demonstrates live view in a way that I could never do myself. Because in 15 minutes, the author of that video builds a real-time clone of Twitter. Now, just think about that. If you could do clone of Twitter with real-time updates in your language of choice, I want to see that. If you can do it, I want to see that. Another video that I posted there as well is a bit longer and a little bit more in depth, but it goes into the soul of Erlang and Elixir. It starts a little bit more in depth, but as you go, I'm not sure if you will be able to turn that video off, because the thing that Sasha Yuris shows there are absolutely mind-blowing examples of how parallelism works for you and with you, thanks to the power of the Erlang virtual machine. Finally, that's really all. If there's any questions left, I'm going to be super happy to try to answer those. And I would like to again thank you for your attention today and hope that we can see each other in the next 2 or 3 weeks on the next Tech Talk.
Thank you so much, Milan. So since it's already closer to the ending time, first, I will like to take this opportunity to thank you again for preparing this awesome presentation, and also helping us with the expansion of the Tech Talk. And I will also like to thank our members, especially Irving, Salim Bhai, Rafi, to help us expanding this to Philippines and Bangladesh as well. Hopefully we'll be having like more members presenting interesting topics in this session. And also regarding this slide and the videos, we'll be updating those, probably host them over Google Drive, and we'll be sharing those contents later on over the channel. So please make sure to subscribe to the channel, TikTok Backend, if you would like to have those materials later. So that would be all for now. So if there's any comment, any kind of question from you guys, please feel free.
I think the presentation was clear enough and very well described. So I think there won't be enough questions.
Thank you so much. I'm happy to hear that. Thank you.
Yeah.
And yeah, of course, like this is a really exciting topic itself, and it's difficult to cover in one particular session. So hopefully we'll be having more sessions in the coming weeks, maybe something hands-on as well. We can have more queries that time too. But if you have anything else from any other member, just last minute we have.
I would be, by the way, happy to organize some sort of, I don't know, workshops on or more casual discussions in Elixir for anybody who's interested in that. And again, the Slack group work group Elixir would be a great place to start that discussion.
Okay, seems like it's fine for now. So I again want to thank you all. Thank you for giving the time. So looking forward to meet you all in probably 4 weeks. So till then, take care.
Thank you so much. Bye-bye.
Thank you.
Thank you.
Bye-bye. Thank you.